Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel. Today's topic of discussion is pressure relief valves. Our objective is to introduce both direct-acting and pilot-operated pressure relief valves and discuss their purpose, construction, and method of operation as applied to fluid power systems. The purpose of a pressure relief valve is to limit the maximum pressure by providing an alternate flow path to the tank when flow in the circuit is otherwise blocked. A pressure relief valve is an important safety device that prevents damage to the system and personnel. Given a fixed displacement pump rotating at a constant speed, flow rate produced by the pump is constant. When in the act of moving a fluid power actuator, flow has a place to go. If, however, the actuator has reached the limits of travel, or if flow is otherwise blocked by a change in valve position, flow has no place to go, and if the stupid pump keeps pumping and pumping and pumping, pressure rises and rises until a weak point in the system, ordinarily a hose or fitting, explodes. An alternative to this regrettable scenario is to purposely design a weak point in the system, known as a rupture or burst disc. The rupture disc is essentially a chintzy piece of metal that is designed to burst at a specific pressure, thus saving the system and any operators in the vicinity any damage. Ordinarily, the outflow of a rupture disc would be channeled via a drain passage back to the reservoir. Lacking this drain passage, a burst rupture disc would save the system from damage, however, spray fluid everywhere. While effective, rupture discs are inelegant one-time solutions to pressure relief, and more sophisticated methods are conveniently available, notably the pressure relief valve. The schematic symbol for a pressure relief valve indicates a pressurized P inlet port and a non-pressurized discharge port T. The P port on a pressure relief valve is ordinarily routed to a system under pressure, typically right next to the pump. The T port on a pressure relief valve is ordinarily routed to the tank or reservoir. Alternatively, these are also known as the primary and secondary ports of the pressure relief valve. The dashed pilot line indicates the pressure relief valve is sensing pressure on the pressurized P port. The arrow on the spring indicates the set value is user adjustable. The passageway linking P to T is normally closed, and at its deactivated state, the pressure relief valve does not allow fluid flow. When activated by pressure in excess of its set value, the pressure relief valve opens and allows fluid flow. When pressure drops to the reset level, the pressure relief valve returns to its deactivated closed state and stops fluid flow. Pressure relief valves are often referenced on a schematic using the shorthand RV, PRV, or if it needs to be explicitly stated that the relief valve is pilot operated, PORV. The purpose of a pressure relief valve, again, is to limit the system maximum pressure by providing an alternate flow path to the tank when flow in the circuit is otherwise blocked. Again, given a fixed displacement pump rotating at a constant speed, flow rate produced by the pump is constant. When in the act of moving an actuator, flow has a place to go. If, however, the actuator stalls out at the limits of travel, or if flow is otherwise blocked by a change in valve position, flow has no place to go. And if the stupid pump keeps pumping and pumping and pumping, pressure rises and rises until the pressure relief valve actuates and provides an alternate flow path to the tank, thus relieving pressure and saving the system and any nearby personnel damage. Consider the simplest of pressure relief valves, the direct-acting pressure relief valve. An extremely primitive direct-acting pressure relief valve can be created with a check valve employing a heavy biasing spring on the poppet. A check valve, if you'll recall, allows fluid flow in one direction, but blocks it in another. The heavy biasing spring modifier holds the poppet to the valve seat with a predetermined force. Given the orientation of the check valve, it would ordinarily allow free flow from the P to T ports. However, only does so when pressure-induced force on the poppet exceeds the force of the biasing spring. Even in the ordinarily free flow direction, the poppet remains seated at load-induced pressures below that sufficient to unseat it, and the direct-acting pressure relief valve remains closed. Only at pressures above that sufficient to unseat the poppet from the seat, the valve opens and provides a relief path for pressurized flow. Pressure in the system is therefore limited to a preset maximum. Alternatively, Consider this configuration of a direct acting pressure relief valve. In this configuration, a moving piston held down by biasing spring obstructs the main P to T passageway. However, a narrow pilot passageway acts on the bottom face of the moving piston. This pilot passageway is the dashed line in our schematic symbol. Given the pilot passageway senses pressure on the upstream P passageway, and Pascal's law states pressure in a confined fluid is exerted undiminished in all directions, pressurized input acts on the bottom face of the moving piston. When pressure-induced force on the bottom of the moving piston exceeds that of the biasing spring, the moving piston is forced upwards, opening a passage from P to T. Similar to our previously examined primitive pressure relief valve constructed with a check valve and biasing spring, at load-induced pressures below that sufficient to unseat the piston, the direct-acting pressure relief valve would remain closed. At pressures above that sufficient to unseat the piston, the direct-acting pressure relief valve opens, provides a relief path for pressurized flow. Pressure in this system is again limited to a preset maximum. The utility of this direct-acting pressure relief valve can be expanded by adding an adjustable knob. The knob's purpose is to change the force exerted by the biasing spring and therefore the pressure setting of the pressure relief valve. This is the spring and arrow modifier in our schematic symbol. Note that direct-acting pressure relief valves often employ a drain passage from the space occupied by the bias spring to tank. If any liquid leaked past the moving piston and filled this space, any accumulated liquid in this region would prevent the full movement of the piston and therefore prevent it from relieving pressure. For this reason, the drain passage keeps this space evacuated. Direct-acting pressure relief valves are simple constructions, and this simplicity is their inherent advantage over the comparatively more complicated pilot-operated pressure relief valve we've yet to discuss. There's not a lot of moving parts in a direct-acting pressure relief valve, and as a consequence, they're fast-acting, and there's not a lot that can go wrong. This simplicity, however, is as elegant as a wooden mallet. Not only are direct-acting pressure relief valves notoriously noisy, the principal drawback is their direct nature. Higher pressure systems necessitate larger, more powerful springs. Additionally, due to their simplicity of construction, the behavior of direct-acting pressure relief valves have something to be desired. In a perfect world, a pressure relief valve would have a clear and defined set pressure above which the pressure relief valve instantly and fully opens, and a reset value below which the valve instantly and fully closes. In the real world, this ideal behavior is far from the truth. Pressure often overshoots the initial set value, as this graph shows. To make matters worse, the regions operating at pressures near the set point, the valve being directly acted upon by a spring whose compression non-linearly influences the actuation force, begins to open earlier than the valve's full open set value would suggest. Given a pressure relief valve, let's say an 800 psi set value, this means the P to T passage might begin cracking partially open at, let's say, 700 psi. Appropriately enough, this is called the cracking pressure of a pressure relief valve. The cracking pressure is the pressure at which a pressure relief valve just begins to open and is a value below that of the full open set value. Direct-acting pressure relief valves have a notoriously large difference between cracking pressures and full open pressures, upwards of 150 psi. Pilot-operated pressure relief valves, as we'll soon learn, not so much. In this case, the direct-acting pressure relief valve does fully open at 800 psi. However, operating at regions between 700 and 800 psi means a decreasing portion of flow is available to the system actuators, since an increasing portion is being dumped to the reservoir, as this graph shows. The difference between cracking and full open pressure is what may cause noticeable decrease in actuator speed as a system approaches the set pressure limit. The differential between cracking pressure and full open pressure is sometimes known as pressure override. In this case, our pressure relief valve has a pressure override of 100 psi. Cracking pressure is something that must be anticipated in a system and accounted for. If a system did truly need to operate at full flow capacity up to 800 psi, the pressure relief valve would have to be adjusted up to 900 psi to account for this valve's early cracking pressure and 100 psi pressure override region. This newer, higher pressure limit may, however, necessitate more robust components, fittings, and conductors. Note, preset, non-adjustable pressure relief valves exist without the adjustable knob. It is incumbent upon any technician employing these types of pressure relief valves to determine if the specified fixed pressure is the cracking pressure or the full open pressure. To account for these undesirable effects inherent in a direct-acting pressure relief valve, consider a pilot-operated pressure relief valve, sometimes called a compound two-stage pressure relief valve. The term pilot-operated is used in both hydraulic and electrical systems, and it kind of means the same thing. A pilot signal is anything characterized by low pressure, low flow rate, low voltage, or low current that controls the actuation of a larger primary device characterized by high pressure, high flow rate, high voltage, or high current. A pilot-operated pressure relief valve makes use of a low flow rate pilot signal to control the actuation of a larger flow rate primary valve. Pilot-operated pressure relief valves can operate at higher pressure and flow rates without the use of physically larger springs. In pressure override, the difference between cracking and full open pressure is considerably less. This does, however, come at a cost because pilot-operated pressure relief valves have a more complicated internal construction and operation. This being said, a pilot-operated pressure relief valve overcomes the principal disadvantage of direct-acting pressure relief valves in that pressure override, the region between cracking and full open pressures, is considerably less, often on the order of only 25 to 50 psi. This means a system employing the use of a pilot-operated pressure relief valve will notice considerably less diversion of fluid operating at regions near the pressure set point. A pilot-operated pressure relief valve therefore allows a more predictable response to a user-imposed pressure limit.